All right, again, like the sex determination, I've shot this one about 3 different times. Haven't liked it 3 different times. Haven't been able to edit it out 3 different times. So I'm just going to make it abbreviated, make it quick, give you the basics that we need to worry about, and we'll go from there. So, phenotypic expression of genes. And we talk, guys, that genotype's going to equal their looks. Genotype right there is their genetics, or the genes that you receive from your parents and the environment. And so I told y'all about the fact that I'm the smallest in my family, and I'm pretty sure my mother kept cooking the same amount of supper at night, even after I left and went to junior college. So, my younger brothers are quite a bit bigger. Now, what we're going to do is we're going to break down, and this E is still going to be environment. But guys, we're going to break the genetic component down into 3 different ones, okay? And the additive is where we have a couple of genes work together. And so, we end up with the effect of one gene is going to affect another. And so we may have an animal that's born with a greater weight at birth. Well, that kind of affects it because it's gonna weigh more at weaning, and it's gonna weigh more at yearling, it's gonna weigh more probably in a mature size or weight. So the additive effects right here are just how one gene kind of affects and works with another. Dominance is complete dominance, and where we have complete, we don't have an additive effect. Okay, so if they're gonna be black and polled like we talked about with the Angus, that's complete dominance. And that's like our qualitative traits we talked about, that we can change those really quick, one generation. Epistasis, and guys, this is interactions. So, we have some kind of interactions with our additive effects here. And that's expression of, one gene adds to the phenotypic effects or expression of another. Right here is epistasis, means there's combinations, and certain combinations have certain effects and certain results. Boom. Types of gene actions. There you go. Non-additive equals complete dominance. Additive is effect one gene adds to the phenotypic effect of its allele or other genes in that genotype. So we're looking at something that's compounded a little bit more than just normal. So you're non-additive. And guys, what we had before, even with Mendel, this one was black. This one right here is black. This one right here was red. So your heterozygote, boom, equals your homozygous dominant. Boom. Complete dominance. Genotypes cannot be determined from the phenotypes. And so with that complete dominance, it's just like we said, guys. These two right here are both black. So we don't know how many of them are homozygous for it or heterozygous for that trait. So a partial or complete dominance. And in this case, we may have one that's black. We may have our red down here. And this in here may be a, kind of like our tiger stripe, or our dark or brown maybe. And so we can just say this is kind of a reddish brown, a dark brown kind of color. And so, it's an incomplete dominance. It's not perfect. We can notice a difference. Now, over dominance, and I'd popped the pics off of this before, but, we ran into the one that I had an example of, and you couldn't see it really good when I printed, but with sickle cell anemia. And so with sickle cell anemia, it was perfect for dealing with malaria, mosquitoes, malaria, etc. And so the heterozygote was greater than the combination or the average of the parents, okay? And so it's actually the best one of it. It's not a full hybrid vigor heterosis we see in crossbred, but it allowed them to be able to defend themselves against malaria with that sickle cell gene. Not sure. I think the Calipes gene, and don't worry, don't get me on spelling there. in sheep was also an example of overdominance. So we'll talk about that a little later when we get into some selection. No dominance. Hey guys, this one right here is going to be black. This one right here is going to be, let's say, white. And this one right here, right up the middle, is going to be gray or smoky. So complete no dominance, meaning a heterozygote is totally independent of the other two in terms of color. So, no dominance, shorthorn cattle. And here's the luxury where it says phenotypic frequency equals a genotypic frequency. So if I've got a big A, and that's going to equal a red. This right here is going to equal, if we wanted to say, it's not shorthorns, but if you said pink, kind of right up the middle, because our homozygous recessive is going to equal white. So this right here comes to a roan. Okay, if you wanted to think about it from a different aspect, pink. So in this case, your genotype, big A, little a, equals your phenotype. So if we got a 1 to 2 to 1 here, we also have a 1 red, 2 pink or roan, and 1 white here. So pretty easy with no dominance. We know what we've got. Phenotypic frequency, and that's just the proportion or the average of the looks. So, you know, what percent? If we had them from back here before, boom. I've got 1 out of 4 red. I've got 2 out of 4 roan. And I got 1 out of 4 white. So that's going to equal a 25%, a 50%, and a 25%. And the same thing here. I've got 1/4 that are homozygous dominant. So I'm going to have 25% for big A. I'm going to have the same 50% big A, little a, and the same 25% little a. So genotypic frequency, phenotypic frequency, basically the numbers are the same. It's just here we identify with a color, and here we identify with a gene type or genetic pool. So, boom. There you go. Come back to old Punnett Square. We end up with that red male, let's say. And then I end up with that white female down here. You know, boom, 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 boom. And then every one of them is going to get a lower A or recessive from the females. So we'll end up with an entire herd of roan. The thing with the roans, and there was a producer and a farm up in, right outside of Louisville, Kentucky. And so every year we'd go, judging team, and we'd work out at this really an old shorthorn ranch up there. And the guy kept wanting for the roans and the roans and the roans. And we just keep these roans around. But every year we end up with a few reds. And I guess they thought over time those roans would breed true. But if we come back from a Mendel deal and we start talking about those F1s, hey, I got a roan here and I got a roan here, and I'm only going to use a roan bull. I'm only going to keep roan females. And so, bull up top, got my female over here. And guess what's going to happen every time you do that? So they were only ending up with about 50% roan. But they were sure hell bent on trying to make it happen. And so same thing, guys. If we start talking about some numbers on it from a frequency, a genotypic, phenotypic frequencies, etc. If we start figuring out 60 individuals here, I got 120 big R's. I got 0 of these little R's in it. So I'm looking at how many big R genes I've got. Down here I got 20 of them that are all white. So, or 10 of them that are all white. So that means 20 white genes for each pair. 0 here. So 200 versus 100. And let's see, I'm looking at 90, 150 total. So 60 out of 150 is going to equal 40%. Boom. 50%. Boom. Okay. So that's strictly, guys, using the number of animals on the phenotypic frequencies. Now, do genotypic frequencies, pretty much the same, because each one has an independent or totally different because incomplete dominance. So we'll work some more equations with that on it later. Gene frequencies, and tell you what, just don't even worry about this. I'm going to get you a couple of exercises that make things just a little more sense at a later date. We got page 4, that didn't print it. Hold on. Let me come in here. There goes your short horns. Boom. There's your extra number there. Boom. Gene frequencies. I'll do the exercises later.